Hello, AP Calculus AB, and welcome back. We are in kind of the second part of Topic 5 where we're practicing our definite integrals. We learned our definition a couple classes ago. We used geometry to find exact areas of certain graphs, but then we jumped into a new area, pun intended, where we now have graphs where the area is not easily able to be found exactly using geometry areas. And so last class we used left rectangular and right rectangular approximation methods to approximate the area under the curve. And all that really was drawing rectangles, either starting from the left side of a subinterval or the right side. And I had mentioned that there are going to be two more approximation methods you need to know, and we're going to touch on those today. So today's lesson should be much quicker than yesterday's since we already have all the basics. So let's get on to midpoint and trapezoidal Riemann sums. To get started, because we're going to be doing our notation a little bit more today, let's go ahead and have you guys try a left rectangular approximation and a right rectangular approximation for the graph of y equals x squared. I would also ask and see if you can do this without creating a graph. So go ahead and give that a shot, and once you're done, unpause and we will see how you did. Ready, set, go. All right, and we're back. I said try to do this without creating a graph. I'm just going to show a very quick sketch of this, and I'll just use this middle piece as my graph. So something like this. We're only looking for from 0 to 2, so it's kind of the right side of this parabola over here, isn't it? So we have 1, 2, and then we kind of have a half and 1 1/2, so we'll do something like this. And I just wanted to show a quick visual here, and then we can go through and try to do this again, maybe without using the graph, but I'll refer back to the graph so you understand what we're doing. So, left rectangular approximation method. We should notice that there are 5 of these x values that make up our interval. If we think about this left rectangular approximation method on each interval, and I'm going to draw in the 5 intervals, or the 4 intervals here, we start on the left. So left, 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 and left. The last interval we exclude 2, because for any left rectangle you exclude the right endpoint. We should also notice that the base of each of these is 1/2, and that's going to be in common to all of them. So one way we could put this is we could say the area from 0 to 2 beneath the graph of x squared dx is approximated by, and then because 1/2 is in common to all of them, we can factor that out. And then to be very creative here, instead of actually finding the y values, think about how you find the y values. You take these 4 x values here that I'm going to show in blue, and you evaluate them in x squared, right? When you substitute in each of these into x squared, you get a height or a y value. So the way I'm going to show that is we'll start with the left endpoint, f of 0, and then the next endpoint is f of 1/2, the third one is f of 1, and the last one is f of 3/2. Notice we're adding 1/2 each time, and we stop 1/2 short of 2. Great. Now I did say you could use your calculator, so let's use our calculator to make this a little bit easier. However, before we do that, we should probably go ahead and set up the right rectangular as well, just so it can go a little bit faster. So right rectangular approximation, I'm going to work down here and use some space. Again, using that approximately, that is required on these type of problems, so that, because we're going to get 2 different answers here with a left and a right. So let's get to our right rectangular. 1/2 is again the same base, but now as we go through, and I'll use green for this one, we are going to be using the right hand endpoint of each interval. So f of 1/2 plus f of 1 plus f of 3/2, and we end on the right endpoint having excluded that left one. And there we go. Now, how do we find their actual values? Well, the equation is x squared, so it really means plug 0 and 1/2 and 1 and 3/2 into x squared, but we can be a little bit more efficient with our calculators. So I'm going to do one of these with the Inspire and the other one with the 84, and you can pick which calculator you're using, but I'll start with the Inspire. So how am I going to do this? Well, I already have the equation graphed over here, f1 of x equals x squared, and there are a couple ways to do this, and this is kind of nice. One way that we can do it is we can, of course, just type out what's here. We can go fraction 1/2, and then we're going to use the name of the function, right? f1 turns bold because that is our function that we graphed previously, and then if this is the left hand, it's going to be 0 plus f1 of 1 plus f2, oops, plus f1 of, oh, and I'm doing poorly here. I'll use decimals just so I don't have to do fractions, of 1 plus f1 of 1.5. And there we go. And we'll get our answer of 1.75. If you wanted to do this slightly differently, you could, instead of having the function graphed, I'm going to go ahead and delete this just so you don't think I'm pulling wool over your eyes. We could go back here and we could take that equation, x squared, and we could actually give it a name. So maybe we're like, we want to call this function g of x. Well, great. We have the option to go to Menu, Actions, Define, Menu 1-1. And it says, what do you want to define? I would like to define the function name g of x as the function x squared. All right. So then how do we do what we did up above without the graph? Well, same idea. I'll create my fraction again. You could, of course, just type out 0.5, probably a little faster. And then now we can just do g. When I type g, you'll notice it's bolded because I defined g as x squared. And then we substitute each of these in. So g of 0.5 plus g of 1 plus g of 1.5, and we still get the same answer. So if you'd like to define your function as a different name, you don't need to use a single letter either. You could say define grant of x equals x squared, and then you'd have to type in the name grant every time, but same idea. Okay. With the 84, you do actually have to have your equation graphed. So I already have y equals x squared graphed. This is y1. And I'm going to go ahead and do the right rectangular approximation for this. So we'll do 0.5 of, and then we do have to use this guy, right? Alpha f4, and you'll see y1 pop up. y1 of what? y1 of, we're skipping the first endpoint this time, 0.5, and so on and so forth. Now, you could probably argue here that it's probably faster to just type in each of these being squared instead of me having to do alpha f4 every time, and you're 100% right. However, if the equation was more complicated than x squared, like x squared plus sine of x minus x cubed plus natural log of x, I wouldn't want to type that every time. So this one would then be a faster way to go. 1.5, and I have one more of these, so alpha f4 of, oops, and I forgot a parenthesis. That will throw things off. So second insert so you don't delete the whole thing. Throw that parenthesis back in there. y1 of 2. And then I had an opening parenthesis to account with because it was 0.5 times all of that. So that's there. Now before I hit enter, let's think. Is this going to be smaller or larger than 1.75? Well, jumping back here to our graph, wherever this went, this is an increasing function, and we're doing a right rectangular approximation. So if we do a right rectangular approximation, I think we can see that all of our rectangles will over-approximate. So this one is going to be too much. So whereas 1.75 was too little, this one I imagine should be larger than 1.75, and it is. It's 3.75. So two answers here. Left was 1.75, and the right was 3.75. Don't forget to get full points for a Riemann sum approximation. You do need to show a sum and a product somewhere, and I have met those requirements. I showed sums, we see all the addition in here, and I also showed a product with the 1/2 out front. But you can't skip showing both of those somewhere, so you can skip steps, but not too many. All right, let's go ahead and pick up where we left off last class. We're going to learn our third method now, the midpoint rectangular approximation method, or our MRAM. And this is so similar to the left and right. It's worth showing because it comes up every now and then, but it shouldn't be anything that is crazy brand new. For each subinterval, instead of starting at the left or the right, we begin at the midpoint. And then we use the height of the graph from the midpoint as the height of our rectangle, and you draw over to both the left and right sides to complete your rectangle. So if you're given some subinterval, and I should probably sketch this graph out first, something like this, right? And they say they want you to go from A to B, and let's sketch in the graph, right? Something like this, and then we start subdividing this out. Okay, and then there's some number of intervals over here. We might remember that to get from A to the next x coordinate, we call this distance in the middle delta x. And so this next point would be A, which is the x value plus whatever delta x is. So we have these two pieces here, and we need to draw from the midpoint, right? So my midpoint's going to go up to the graph, and then I draw over and down to get a rectangle where the base is still delta x, but the height is something different. One of the nice advantages here is now you're over approximating on one side while under approximating on the other. So for many graphs, this midpoint might get you a much better answer than our left or right rectangular approximation method. Just a friendly reminder on how to find the midpoint. You can, of course, if you look at 1 and 2, you're like in the middle of 1 and 2 is 1.5. There's the midpoint. Yay. But if you are asked for the midpoint between 7.1 and 7.6, maybe that's too easy, 7.065, then you're like, oh, that one's a little trickier, I'm not sure, then you can always find the average, right? And so if you wanted to find that midpoint, you could take one endpoint of your interval, A, add it to the other midpoint, in this case, A plus delta x, and then divide them by 2, right? We are averaging them. You add up those two, divide by 2, and it finds the middle, or the mean if you would like. This doesn't simplify to anything too crazy. 2a plus delta x over 2. If you wanted, you could say that this is a plus half of delta x. But either way, it doesn't simplify to anything too recognizable. Midpoint rectangular approximation method. Let's try one of them. We are now going to approximate the area for f of x equals x squared from 0 to 2 using 4 subintervals. Oh my gosh, it's just like the opener. I wonder if we'll get either of those answers. Well, we have our friendly little graph. I think we only need to do the first quadrant. As we saw earlier, it's just part of a parabola. Here's 2, 1, and then our 0.5s in there. Okay, and I should probably write those. So we have 1/2 and 3/2. Okay. How do we do this? Well, as before, the base of each of these, and I should probably go through and show what we're going to do. We're going to be creating, let's do our intervals in blue, something like that. We're going to be creating our rectangles using the midpoint of each of these intervals. So it doesn't matter if you start on the right or the left. The midpoint is right about here. We draw up to our graph, over and down, over and down. Same thing over here. Here's the midpoint, draw up, and something like that. Here's my midpoint again. Now I'm saying here's my midpoint. We should realize, of course, that I haven't actually given a value to the midpoint, but using halves is pretty easy, I think. So we have, let's see, there's my first one. I'll do different colors so we can kind of see the alternating pieces going through here. And then my last one is this little guy down here. Okay, so if we want to add this up, we're going to do the same as before. We'll say the area from 0 to 2 of x squared dx is going to be approximated by, the base again is 1/2. That's very nice. And then how do we find the midpoints? Well, because this is easy enough, you could just say, well, I know that the midpoint of from 0 to 1/2 is 1/4, right? So f of 1/4. Then you could say between 1/2 and 1, that's 3/4. Okay, and then for the next one, between 1 and 1.5, I think that's going to be 1 1/4 or 5/4. And don't we see a pattern now? 1, 3, 5. I bet the last one is going to be 7/4. And in fact, that happens very often. It happened up above, and you might not have even realized it. This adds by 1/2 every time. That adds by delta x. Exciting. Well, this one also adds by delta x. So delta x was 1/2. We are adding by 1/2 every time. And if you add the same number, eventually a pattern emerges. Okay? We should probably go through and use our calculator to calculate this. Just so I don't show any preference, I prefer the Inspire. I'm going to show you Desmos for this. And on Desmos, I already have the equation graphed over here. Okay? And we're just going to go through and say it was 1/2. And then we do f of, and let's see, we had 1/4, didn't we? And then Desmos always trips me up with my fractions. F of 3/4 plus f of 5/4. And the last one, f of 7/4. Great. And we end up with 2.625. As you may have guessed, this approximation, 2.625, is somewhere in between the left and the right rectangular approximation method. The left is well below, the right is well above, and the midpoint is somewhere in the middle. Now you might say, well, wait, is this exactly it? And it turns out no. This little sliver over here that over approximates is not the same size as the sliver over here. The sliver is a little bit bigger just based on how fast the graph is going up. So they're not exact, but you can also see that maybe they're canceling each other out-ish. Right? A little below, a little above gives us, probably a more accurate representation. Now, a midpoint is not always a more accurate approximation, but many times, especially if it's a smooth curve that's strictly increasing or decreasing like this, it might be. All right, on to our last approximation method. This is everyone's favorite because they start to remember that they don't remember geometry. We are on to our trapezoidal approximation method. What are we going to do? Well, we're going to make trapezoids. Now, realize that there are two ways that we can see trapezoids, maybe more than that. A trapezoid is just defined as a four-sided figure with one set and only one set of parallel bases. So this was not a trapezoid because these guys right here are parallel, but these are also parallel. Those are two sets of parallel bases. Now, the most common trapezoid you see is something that looks like this, and you can see our two parallel bases. Then a lot of times these are the same, right? They're not parallel, but they are congruent to each other. And this is our regular trapezoid, or there are various names for it. We are not going to see that today. In fact, our trapezoids are either going to, depending on how you turn your paper, look like this, with a right angle here, and we see our set of parallel bases, or maybe even more accurately, they are going to look like this. That is indeed a trapezoid. Now, we should also define the various pieces of this. When we talk about the base of a trapezoid, we mean the parallel side. So a lot of times we'll see like base 1, base 2. It doesn't matter how you write them here. And if we write with the side ones, we always do this with our parallel sides, base 1, base 2. Or if it's standing upright, maybe base 1, base 2. And then the height of the trapezoid is always given by the altitude drawn between the two parallel bases. Altitudes are going to end at a right angle, so in this case my height would be this guy. That's the height of my trapezoid. These right trapezoids are a little easier because we can see the height. And this is kind of strange, but because when it's standing on itself, there is the height, even though it's moving horizontally instead of vertically. So let's keep that in mind and see what the graph looks like. Okay, graph-wise, we are again going from A to B, and here is the graph, something like this. And we, of course, have a few subintervals in here. Great. Now, to work this for each subinterval, we need to start at both endpoints. So I'm going to go with my first subinterval, this a plus delta x that's right here, and we are going to draw up to the function from both of the endpoints. Those are the bases of my trapezoid. Then we connect and connect. And now we can see a trapezoid here that, strangely for everything we've done so far, has base 1, base 2, I wrote 2, 2, whoops, base 2, and a height. So instead of considering this guy down here a base, now we are considering it a height, but same idea. And then if I wanted to draw one more, we would draw up from one side, up from the other, connect these, connect the height, and now we have our base 1 and base 2. Well, and that's all wonderful and grand, but we didn't actually talk about how to find the area of a trapezoid. Well, it turns out that pretty much any area of one of these four-sided figures is all about the same. It's all base times height. The main issue, though, is that although there is one height, there are two different bases. But it turns out that if we find the average of these bases, so maybe we shorten this guy a little bit, but elongate this guy a little bit, right? They kind of meet in the middle, one gets shorter, one gets longer, then we have a nice rectangle, which is just base times height. So how do we even out those bases? we find the average of the bases. And so that is why the area of a trapezoid is given by the base, and the base needs to be the average of the bases. So I'll write this two different ways. Sometimes you see it as base 1 plus base 2 divided by 2. That's the average of the bases times the height. Or, and I prefer this method, I just don't like having everything over 2, I would write it as 1/2 base 1 plus base 2 times the height. You do need to have that memorized, or just realize it's the average of the bases times the height. We will be using it often. I almost guarantee you will need to use this at least once on the AP test somewhere. All right, our last example for the day. Using our trapezoidal rectangular approximation method, determine the approximate area for f of x equals x squared on the interval 1 to 9. Oh, we've picked up our interval this time. Okay, I think we'll be all right. So here we go. We need our graph, and again, you don't need your graph, but the first couple times you do this, you should probably draw a graph till you get comfortable. We have our parabola, looks something like this, doesn't have to be perfect, and I'm going to go out to 9. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9. That's pretty good. All right, good. And actually, maybe not great because I need to see this one a little bit more closely. So I know it's not quite a parabola, but I think this space down here is the trickiest spot. So let's see what we can do. There are 4 subintervals here. 4 subintervals. Let's see, dividing 9 into 4 subintervals. Oof. But we're going from 1 to 9. Oh, that's much better. So maybe we should take a quick look at delta x and not forget how to do that. We take the length of the interval, 9 minus 1. Right, the whole interval is just this guy, excluding 0. And then we divide by 4. So 8 divided by 4 is 2. So each interval, starting at 1, has a length of 2. There we go. And that, I think, gives us 4 subintervals. That's looking better. Alrighty. And now we look at our trapezoids. So trapezoid-wise, I'll try to do alternating colors here. We have our first trapezoid, like so. And then we have our second trapezoid. And then our third. And our last. That's supposed to be way up here, so we'll just pretend the graph goes up there. Ha. Great. 4 trapezoids, and now we start finding the areas. Now, to find the areas, there is, of course, a shortcut again, and so I'll show it to you twice just to make sure you're comfortable with this. But let's start labeling all the pieces, at least at the beginning. I think normally we wouldn't do this, but just for the sake of clarity, so we have base 1 and base 2, and we have our height over here. Notice that the height every time is 2, right? My bases, though, are going to be defined by our function. So if this is 7, and this is 9, and 5, 3, and 1, if I want to define my height here, then the height, or this base 1, is going to be f of 7, right? We substitute in 7, and it gives us that point. This is 7, comma, f of 7. And same over here, base 2 is going to be f of 9. And then look at what happens if we do to the one right next to it. This is also going to be f of 7, and this will be f of 5. F of 5 repeats again in f of 3, and f of 3, and then this guy over here is f of 1. And now we can start putting together our trapezoidal formula. So the long way around it is to write out the area of every trapezoid. So we're going to approximate the area underneath the graph of x squared, not from 0 to 2 this time, that's silly, from 1 to 9. Okay. And it goes like this, right? Our first one is going to be 1/2 times base 1, so base 1 is going to be f of 1 this time, so f of 1 plus f of 3. That's the average of the bases, right? And then times the height, which is 2. And then our next one, and we'll start to get the pattern, I'm going to stop using colors, is going to be f of 3 plus f of 5, that's our first green one, times the height of 2. And then our third one is going to be 1/2, and we have f of 5 plus f of 7, again times the height of 2. And last but not least, f of 7 plus f of 9 times 2. And you'll notice as we go through, we do use every x value on the interval. In fact, we used every x value twice. We used f of 3 twice, and then we used f of 5 twice, and so on and so forth, but we only used the endpoints once, right? F of 1 and f of 9 only appeared once, and that's because nothing borders them on either side. Good. So we go through, and we could totally do that, but also notice that there's a way to simplify a bit, right? We could factor out the 1/2 that's common to all of them, and the 2 that's common to all of them, and maybe rewrite it like so. F of 1 plus, then there are 2 f of 3s, so 2 of those. There are 2 f of 5s, 2 f of 7s, and only 1 f of 9. And that will give us our trapezoidal approximation method. You'll notice that even those will cancel out, and then I think it would be very quick to use our calculator to come up with that final answer. So again, I'll switch back to Desmos, probably faster for me to type. You can use your own calculator, and let's see what we come out with here. So this is going to be, and notice I define this as f of x. If I were to do y equals here, it wouldn't be quite as easy. So those canceled, and it was f of 1 plus 2 of those f of 3s plus 2 of those f of 5s, 2 more of those f of 7s, and 1 of those f of 9s. 248 is our approximation, so approximately 248. Great. So that's really the end of our examples for today. There's a quick conclusion and connections at the bottom of this, and then you're going to have 2 pages of practice questions where I have the solutions posted on Teams. So let's finish these connections, and you guys can keep on living your lives and practicing more calculus now that we're just about done. So the first question is, what happens if you average the areas of the right rectangular approximation and the left rectangular approximation? Well, ultimately what we're doing here is we have a graph, right? And let's say that we have A and B, and then this one is, of course, A plus delta x. And there's 2 ways to create this rectangle. We can create the rectangle from the left side, and so that rectangle would have an area, right, of delta x, which is your base, and then your height is f of a. That's like our left rectangular approximation method. That's that piece right here. Okay, and then, so let's say that maybe that one over approximates. And then you also have a graph that you start on the right, and maybe the right one looks like this. Well, this one again has a base of delta x, but now the height is found by substituting a plus delta x. And so this rectangle, with probably a different area, is a right rectangular approximation method. To average 2 things together, you add them together and divide by 2. So what happens here? Well, let's see. I see 1 term, 2 terms, but it looks like delta x is in common. So let's maybe factor out that delta x really quickly and then see what we have. So we have delta x times f of a plus f of a plus delta x, all of that divided by 2. Or maybe rewriting this once more, couldn't we treat this as 1/2 times f of a plus f of a plus delta x, all of this times delta x? And then if we maybe gave these different names, delta x kind of looks like a base here, but what have we seen before? When we add the 2 heights together and divide by 2, that's like the average of the heights, and then multiply by the base. Couldn't we maybe even think of this as base 1, base 2, right? Those 2 are parallel, base 1, base 2, and then we're multiplying by delta x, which normally is a base, but if you turn your paper sideways, isn't that a height? And in fact, if you average those 2 areas together, I think you come up with the formula for a trapezoid. And so interestingly enough, if you average the results of your right rectangular and left rectangular, instead of being the midpoint, they actually end up being the same as the trapezoidal approximation, which I think is pretty interesting. Okay, finishing off today, we discussed last class how left and right rectangular approximation methods can over or under approximate various graphs. Today we're going to do the same for midpoint and trapezoidal, and all we're going to do is look at positive graphs, a little bit easier. You can recreate these experiments with negative graphs, but we're just going to look at a positive graph here, and we're going to do one that is concave up. Okay, and then we're going to do a second one that is concave down. All right, and I'm just going to use kind of each side. I probably should have done two graphs, but I didn't want to. And we're going to go ahead and look from A to B like so, and we'll just subdivide a couple intervals like this. And we'll first maybe look at our trapezoidal approximation on this. I think you can probably convince yourself that wherever you draw a trapezoid, that you're going to be over approximating, right? And I'll just kind of keep a reminder that a trap is going to over approximate. What about a midpoint? Well, if I used a midpoint here, looks something like this. This triangle in here looks bigger than the other one, so this midpoint I think is going to under approximate. If we did this over here, again, a little bit harder to see, especially if I'm not a good artist, but maybe this one's the easiest to see. Right? This one has a really big chunk missing, and we're only gaining a little bit, so I'm pretty sure this midpoint is an under approximation. Okay. So go ahead and try the other graph and see if you come up to similar conclusions. Just like last class, you should expect them to be flipped. And then once you've tried that, come back together and we'll see how you did. Okay, so just verifying really quickly, we'll again split this into a couple subintervals. Doesn't need to be perfect. They don't even need to be equal here. And if we looked at a trapezoid, so we draw up, and this one's a little trickier, but you can kind of see that it under approximates, or maybe we can even try one more over here. Here are my parallel bases. Trapezoid under approximates. So I'm pretty sure my trapezoid will under approximate this time, and my midpoint, I'm assuming, will over approximate. Well, let's see. If we did something like this and we drew up, and then we went over to both. Yeah, it looks like there's a pretty big sliver missing up there. Maybe we did something like this. We drew up, and then we went over here versus over here. Yeah, definitely a bigger sliver out there. So it looks like my midpoint is going to over approximate. Now again, I don't have these memorized. If they ask us, I just draw a graph, draw one of these, and see if they over or under approximate. But here we go. If a graph is concave up and positive, then the midpoint approximation is an under approximation, while the trapezoidal approximation for concave up is an over approximation. Nothing you need to memorize, just be willing to draw a quick graph and you will get your answer. So thanks for learning about all these approximation methods. What we're going to do over the next few classes is try to move closer to how we can do a better approximation. And we're just going to focus on these four, though there are others. And we are going to try to see what happens if we use more subintervals. How can we maybe even find the exact area using a lot of rectangles? And we will try to tie all of this back to antiderivatives eventually. I'm excited to have you back next class.